Well, let us resume with our last lecture. During this lecture, we will consider the case of constructing far from CMC solutions for charged fluids. Let us recall that in our last lecture, we presented a David Maxwell construction for far from CMC solutions for the vacuum Gauss-Codazzi constraints in the case of three-dimensional closed manifolds. And the idea here is to try to extend those results in a few directions. First, this idea of considering a good and interesting case of non-vacuum case given by a charged perfect fluid. And this, as we have already commented along the course when we presented the appropriate constraint system, this imposes some difficulty from the beginning because this is the conformally formulated system that we already described in previous lectures. And the case of a charged fluid introduces one further difficulty, that is that the system, in order for the system not to lose its defining properties, there's no way to decouple the system. So even under CMC construction, under CMC assumptions that, for instance, would kill this term here, so this wouldn't be here, the system would be completely coupled, even under CMC assumptions. So from the beginning, we see that these systems rely on our understanding of how to deal with this kind of fully coupled systems that involve not only Lichnerics and the momentum constraint, but further equations, in this case, this quite a simple equation that we are adding arising as an electric constraint. Okay, so this increases one level of difficulty in the analysis, and the idea is to present the analysis in this case now. So let us recall some of the notation here. Here, this coefficient in the Lichnerics equation now incorporates this contribution from the energy densities associated with the fluid. Here, recalling that this mu parameter is the energy density associated with the fluid, P is the pressure density. This is related with the initial data of the velocity field of the fluid, and this U tilde gamma. And we also have as energy contributions given by the electric field and the magnetic field, recalling that this E tilde stands for the electric part of the electromagnetic field, and this F tilde for the magnetic part of the electromagnetic field. And we have a momentum contribution due to the electromagnetic field. We have momentum contribution due to the derivative of the mean curvature and due to the fluid here. I'm recalling that this Q tilde, it's a rescaling of the charge density associated with our fluid. Good. So these are the definitions that we were commenting before. And let us also recall that we have already formulated the boundary conditions associated to black hole initial data that's applied to this kind of fully coupled system. And they are given by these boundary conditions here. Let us recall that they appear as boundary conditions by imposing this convergence condition on the expansion coefficients, and these convergence conditions here is related to the convergence of future pointing light rays across this boundary surface. And it represents marginally trapped boundary conditions. So this is going to work as a boundary condition for the Lichnerics equation. This is going to work as a boundary condition for the momentum constraint. We have added here a boundary condition for the electric constraints, which basically is prescribing the normal component of the electric field along the boundary. And let us recall that these boundary conditions had to be complemented by these a priori conditions in order for the solution to actually represent a solution with marginally trapped surfaces as boundary conditions. And this last condition is a link between two free parameters of the problem, so it doesn't impose an a priori strong restriction, but this is more subtle because this function v that appears here has to a priori be a bound by above of the conformal for the conformal factor. So this is something that when we analyze the system, we need to be careful if we want the solution to represent a marginally trapped surface boundary condition, it must satisfy this a priori bound along the boundary. And here we also can remember, can recall the notations associated with the coefficients. So theta plus and minus stand for the expansion coefficients. This nu hat stands for the outward pointing gamma unit normal along the boundary. Gamma stands for the mean curvature of the boundary with respect to minus nu. This is the prescribed value for the normal component of the electric field along the boundary. And this is actually going to translate into a Neumann type condition for the electric potential after we go through a Helmholtz decomposition. The idea is that the electric constraint above is posed as a divergence for the electric field. And we're going to try to rewrite this as a second order PDE on the electric potential. And for this, we're going to apply a Helmholtz decomposition. And here, the idea is to try to use most of the techniques that we have been developing through this course. So we're going to analyze these systems, these boundary value problems associated with initial data for charged fluids on the case of asymptotically Euclidean manifolds, and with the idea of representing solutions that have marginally trapped surfaces as boundary conditions. So we are putting together many things that we have been developing along this course. And the results that we are going to present are contained in this paper by myself and Professor Jorge Lira. Here, the results are more general, but a particular application is to the case of this kind of electromagnetic constraints. Good. And everything also is described in detail in the lecture notes. So let us start with the Helmholtz decomposition so as to rewrite the electric constraint as a second order PDE. So we have an asymptotic Euclidean manifold. We are keeping always the level of regularity that we had already been dealing with. And let us fix a weight parameter here and introduce a few operators. The first one is basically the gradient taken with respect to symmetric gamma with an additional Neumann condition. The second operator here, this L, is basically the Laplacian with Neumann conditions. And recalling that we are dealing with the negative Laplacian, so the Laplacian is basically divergence of the gradient. And we can rewrite the Laplacian as this composition of these two maps. The first one here, this L1, is this gradient with Neumann conditions that we have already introduced above. And the second one is going to be the divergence with the identity acting on the boundary. Okay. So it's clear that we can rewrite this operator L in this fashion, and the idea is to be able to apply to it this theorem. This is a functional integral result that basically tells us that if we have two maps here, T and S, and the range of one lies within the domain of the second one, then we can form the composition, and these two properties become equivalent. The first one says that the kernel of the composition has the same kernel as the first map, and the range of the composition has the same range as the second map. And the second property says that actually the intermediary space, here denoted by Y, is split between the image of the first map and the kernel of the second map. So for us, the idea is to be able to apply this theorem. And in particular for us, our composition here is going to be precisely the Laplacian with Neumann conditions. And this intermediary space Y here is going to be this space, this Banach space. And here is basically where the electric one form lives. So we're going to split that space and then apply the splitting to the electric one form. So this is the Helmholtz decomposition. So given an asymptotic Euclidean manifold, our level of regularity, and we impose now this parameter rho, this weight, to be in this range that we already saw that this range is special, is where our elliptic operators have good mapping properties. And in particular, the Laplacian, for instance, with Neumann condition becomes an isomorphism when acting on spaces that use this weight parameter. Well, in this setting, the idea is that we have this decomposition here. So this intermediary space where our operators act. So this is this space is split between the range of the gradient and the kernel of the divergence. That's the idea. So the point for us is going to be that this space is basically going to be where our electric one form is living, and we want to split this as some electric potential plus some one form that lives here, and therefore the divergence of this is going to be zero, and the electric constraint is going to appear as a Laplacian on the electric potential. This version of the composition is quite straightforward to prove because we want to apply the functional analytic results described above. So we need to see that the kernel of this Laplacian with Neumann condition coincides with the kernel of the gradient, and its range coincides with the range of the divergence. And as we said, we know that this Laplacian with Neumann conditions acting on this between these spaces for this range for the parameter rho becomes an isomorphism. We know this from previous lectures. And we can use this now to prove these two conditions. First, it's clear that the kernel of L1 is going to be contained by construction, by definition of the kernel of L. But since L is injective, acting on our spaces, acting on this space, it's injective, then the kernels are both empty and they coincide. And something similar happens for the range of these maps, because we know that the range of the map L is going to be contained on the range of L2 here by definition. But again, since the Laplacian here is an isomorphism between these spaces, then the complete target space is covered by the range of the Laplacian, and then the range of the divergence is included in the range of the Laplacian, and this becomes an equality. And therefore, all this follows from the isomorphism property associated with the Laplacian with Neumann condition in this case. The above theorem actually holds under weaker conditions. This is something that is explained both in our paper with Jorge and in the lecture notes. But in those cases, the proof is more involved. And for us, the results, these results are enough. Just we wanted to comment, for instance, that here in this weaker scenario, some subtleties arise even if we don't have a boundary. In the case that we have more than one end, and this is related with the fact that functions, harmonic functions, in this case, may be non-constant, and so things that can be in the kernel of the Laplacian may not be in the kernel of the gradient. And we saw this result, we used this kind of results, and we are going to use them again in order to prescribe the values of our conformal factors at infinity when we worked in asymptotic Euclidean manifolds. We call that in that case, the idea was that we have our conformal factor and we split our conformal factor as some unknown that decays at infinity and some harmonic function with Neumann conditions that tends to some prescribed values at infinity. And for instance, if we had two ends, then we could prescribe two positive constants, for instance, at infinity, different constants in each end, and the resulting harmonic function that tends to these two different constants will not be constant. And therefore, we see that certain subtleties are going to arise in those cases. All this can be confounded in our paper, but for us, this is enough. So the idea is to apply the above theorem to the electric one form. In this case, the parameter rho coincides with our parameter delta, and we know that we are always going to consider delta in this range where we have good mapping properties for our elliptic operators. And therefore, we split our electric one form as an electric potential and a one form that has this zero divergence property. Since the electric constraint is given by taking the divergence here, we see that the divergence here is going to be killed by this condition, and we're going to get the Laplacian, and therefore the electric constraint is rewritten as this second order PDE. And therefore our PDE system is going to be posed on the conformal factor, the electric potential, and the vector field X. Explicitly, our system is given by this system 156 and 57. And here we have rewritten the electric constraint using the electric potential. Good. And we are going to intend to solve now this system on asymptotically Euclidean manifolds. And recall that we always have to have in mind these two conditions, that if we intend for the solution to represent black hole initial data, and for us that's to say that the boundary conditions are marginally trapped conditions, then we have to choose our initial data a priori satisfying this condition along the boundary, and we need to be able to satisfy this a priori bound for the solution, for the conformal factor. Good. And well, since V is a datum, what we have to keep in mind is that, well, part of our task is going to be able to guarantee this a priori bound. And the strategy here is quite similar to ideas that we have been discussing in simpler situations. So using certain intuitions that we use, that we have from the analysis of the Lichtenberg's equation, first we are going to rewrite the Lichtenberg's equation for this curly phi, where this curly phi belongs to a weighted space that decays at infinity. And so we are splitting again the conformal factor as some harmonic function which has Neumann boundary conditions and is asymptotic to specified constants, positive constants at infinity. This relates to what we were discussing around the Helmholtz decomposition. So we do this splitting, and then we rewrite the Lichtenberg's equation both for this curly phi. And here we will introduce this vector bundle. Basically, this first factor is related with sections here are related to our functions phi. Sections here are related with our electric potential, and sections here to our vector field x associated with extrinsic part of the with the traceless part of extrinsic curvature. And we were going to consider these W2P delta sections of this vector bundle. And therefore, we can consider the principal parts here of this system given by these linear operators with these boundary conditions. And denotes all of them collectively by this operator P that acts on sections of this vector bundle and gives us these results after applying our principal parts and their corresponding boundary conditions. Good. And the idea is to do the same for the right-hand side. So the idea is that we are going to denote, for instance, here the right-hand side appearing in these equations and also appearing here by this function f that is going to take our conformal factor, electric potential, and x, and give us the corresponding right-hand sides of each of these equations and boundary equations. And with this notation, we can write our system compactly as this equation here, 158. And at this point, the idea is to be able to solve this equation by iteration, by solving sequences of linear problems. But for this, we know that we need certain invertibility properties associated with the linear parts. And also from our analysis on the Lichtenberg's equation, we know that we are going to need certain monotonicity properties associated with the Lichtenberg's equation in order to trap, for instance, our conformal factor between certain barrier functions. And with all this in mind, we are going to present what we call a shifted system. So recall that we are rewriting the Lichtenberg's equation in terms of this curly phi because omega is harmonic and has also Neumann conditions, so it doesn't interfere here. And what we are doing is basically on the Lichtenberg's equation and on its boundary conditions, we are introducing these shifts here with the idea of imposing that these functions a and b have to be non-negative, and therefore we know from the properties that we described associated with the Poisson operator with boundary conditions that these operators are going to be isomorphisms. And therefore, the idea here is this condition is ordered to preserve the isomorphism property of the linear parts here. And also, these functions are going to give us some freedom to gain certain monotonicity properties when we solve linear problems. The idea is going to be similar to the monotone iteration scheme. So if we start here with some prescribed data on the right-hand side, then we can then use the properties associated with the linear operators to begin an iteration procedure. And the idea is to extract a fixed point in this process. So we're going to analyze this shifted system, where, as we were saying, these functions are chosen so as not to spoil the isomorphism properties associated with the Laplacian, with Neumann conditions, recalling our splitting for the conformal factor. And here we are going to keep our notation. So we're going to denote here the right-hand sides, the linear operators appearing here in the right-hand sides by this P sub AB. And the right-hand sides by this boldface F sub AB, acting on sections of our vector bundle. And therefore, we can write the shifted system now by this expression. And now we know that these first two operators are isomorphisms between the corresponding spaces by choosing our weight parameter to be in this interval. And furthermore, choosing our regularity to be a little bit higher, we know that this condition excludes the possibility of conformal killing fields decaying to zero at infinity. We've seen this in previous lectures. So all the operators involved in this left-hand side are invertible for these choices of spaces. And therefore, we can start with some datum here, psi naught, for instance, and generate a sequence given inductively by solving a sequence of linear problems. And this is what we are going to try to do. This is the main strategy. And then the idea is to extract conversions. So if we are able to extract conversions in the original topologies, then due to the continuity of all the maps involved, the limit point is going to solve this equation, the original equation, without the shifts. And furthermore, from our construction here of the conformal factor, this once again recalling this and the fact that omega is harmonic with Neumann conditions, then the solution to our PDE system that involves this curly phi is actually going to solve the conformal problem. Good. So this is the strategy. And in order to apply this kind of strategy, we need some further mapping properties associated with the coefficients of our system, in particular to those coefficients that introduce coupling between our system. And again, in order to try to simplify notations a little bit, let us recall this is our relevant vector bundle. And here we are typically going to denote sections of this vector bundle in this way. So we have the first associated with the conformal factor. And then we are denoting this y by the combination of the electric potential and the vector field x. Okay, and we are rewriting our system in this fashion. So these are the equations on M. This is the equations on M, and these are the boundary conditions on the boundary sigma. For us, this is our Lichtenberg's equation written in a generalized form, where maybe more coefficients we are assuming could depend in principle on the other fields of the problem. These are the other two equations coupling to the Lichtenberg's equation. In our case, the electric constraint and the momentum constraint, the boundary condition for the Lichtenberg's equation, and the boundary conditions associated with the other equations. And the other equations, in our case, both the electric constraint and the momentum constraint, this operator represents continuous linear elliptic second order operators with boundary conditions which act between these spaces, which are invertible for these choices of our parameters. In particular, imposing a lower bound here, we know that all our operators are invertible. Good. And this also suggests possible generalizations that are dealt in our paper with Professor Jorge Lira, systems that basically have this form, maybe with more equations coupled. For instance, if we were coupling more Yang-Mills equations, as long as the equations that couple to Lichnorovics satisfy this kind of mapping properties, as long as the mapping properties that we are going to describe below that are satisfied by the case of the electric constraints, the electromagnetic system, then these potentially larger systems actually share most of the same properties than this model system that we are analyzing right now. Good. So the first of the properties is this property that we call by boundedness property. So if we have our asymptotic Euclidean manifold with our regularity assumptions, this is the system that we are analyzing. We impose our coefficients to be in the right functional spaces here. And the idea here is to be able to obtain this kind of global estimates. So we fix certain radia, this radia m sub yi, in each of our functional spaces. For us, these are related with the electric and the momentum constraints. So we have balls in the corresponding functional spaces with this radia. And we take the sum of our radia here. Then for our system, what we can see is that there are functions here in LP delta minus 2, and also functions on the boundary here belonging to this trace space, and certain constants which are independent of the element y that we take in these balls. That take the product of these two spaces that satisfy these conditions. So basically, these are all conditions on the coefficients associated with the Lichnorovics. So the idea is that the coefficients on the interior are bounded by some LP delta minus 2 function for uniformly for any element y in this ball. And the coefficients on the boundary are also bounded by some function on this trace space. And their norm is actually bounded by certain constants. So this is the idea. We can get uniform bounds for any elements of our functional spaces as long as they are inside these fixed balls. Okay, that we fix the radia a priori. Let us establish this for our system, and under our functional hypothesis, they are actually tailored so that all the coefficients that don't introduce coupling already satisfy these properties. So for all these coefficients in the Lichnorovics equation, this is trivial. So we actually have to analyze only these two coefficients that introduce coupling. And explicitly, these coefficients are given here. So the first one introduces coupling with the momentum constraint, and the second one with the electric constraint. And using our functional hypothesis and the multiplication properties of Sobolev spaces, we know that these two coefficients are actually in these spaces. And the idea is to apply these estimates that work for any function, any tensor field, any section U in this space W1P delta minus 1 for our choice here, recall P greater than N. That says that actually we can bound pointwise. Recall that we have a continuous embedding. These sections are going to be continuous. So we can bound them pointwise by this expression here. Their norm, and this function R is going to be any function that agrees with the radial function near infinity in each end, and this radial function is computed with our one of our end coordinate systems. Good. So the idea is to apply these estimates to these expressions. So first, for instance, if we consider the case of K tilde here, one can first bound these expressions concerning the conformally derivative by the first derivative of the vector field. And also it is easy to see this first estimate here. And now here we apply these estimates to both terms. And this makes appear this function R. And since we are assuming that X belongs to one of these balls, which are these balls are contained in W2P delta, then this first term is bounded by the radius of our balls. This is bounded by hypothesis. This is a free datum. And then we have these functions here. And what is important for us is that these functions here are actually in LP delta minus 2. So the right-hand side here is in LP delta minus 2. And we have found the corresponding function f for that coefficient. And since the structure of this R coefficient is quite similar and everything here satisfies similar functional hypotheses, then a similar reasoning proves the same result for this E tilde. And therefore, for these two coefficients, things work. And for the case of coefficients that don't depend on that don't introduce coupling, everything follows from our functional hypothesis. And in the case of the boundary coefficients, none of these depend on either f or x. So this lemma is established for our system. And then we need this further property that is, it's a kind of convergence property, and we refer to it as a compactness property because it allows for a compactness argument in the main existence theorem. So if we again consider the same system with the same functional hypothesis and as in the previous lemma, then given a bounded W2P delta sequence, and if we give some delta prime that is between delta and 0, and we assume that our sequence converges in C1 delta prime to some element here y, then it holds that all of the coefficients of the system actually converge in LP delta minus 2 or in the corresponding trace space, okay, for the boundary coefficients. Good. So this convergence property is going to be important for us in order to establish conversions in our iteration scheme. So again, let us show this for the case of our charged fluid system. So we have our sequence satisfying our convergence hypothesis here. And through direct computation, one can see these first estimates holds. This is a very direct computation that can be checked. And then here we apply again these Sobolev embedding properties, the same kind of property that we used above in order to estimate each of these coefficients. These coefficients here give us this function appearing in front of everything. And this one here using Sobolev embeddings in order to form this C0 delta prime minus 1 norm, give us this other factor. And we have each of one of these in each term. And again, since delta prime is below 0, we see that these functions that are in front of these constants actually are in LP delta minus 2. So we can actually integrate here in order to get the norm. And we're going to get a constant here again in front of everything. And the C1 delta prime convergence is going to show us that the right-hand side goes to 0 since this sequence is supposed to be bounded. So this is bounded, and this is going to 0 by hypothesis. Okay. So we see that this coefficient that introduced coupling satisfies this property. And the same reasoning again proves the same property for the coefficient E tilde that we saw that is quite similar to K tilde. And these are coefficient that now appears in the momentum constraint introducing coupling also satisfies this condition following the same kind of arguments. And this convergence property is going to be satisfied trivially for any coefficient that doesn't depend on f or x. Okay, so for all the other coefficients of the system, and also for the boundary coefficients that don't depend on f or x, this property follows straightforward. Well, now that we have all our mapping properties, the objective is to use the these mapping properties, in particular the boundedness property, to allow us to provide certain monotonicity properties associated with the corresponding Lixovics equations. And this is going to be important for us in order to trap our sequence of conformal factors between appropriate barriers. And then the idea is to first show that the sequence is bounded, and this is going to be appealing both to elliptic estimates and again to the boundedness property, and then use the compactness property in order to be able to extract conversions in the right spaces. And the piece that is still missing here is the right notion of barriers. Something that we commented in our previous lecture is that conventional barriers don't work here because in this kind of iteration scheme, our coefficients are changing at each step of the iteration process, and the barriers depend on the coefficients. So we need some stronger notion of barrier. And we're going to introduce this notion of strong global barriers. So the idea is the following one: consider the Lixovics equation associated to our conformal problem that is generically modeled by a boundary value problem of this form. And here y for us is given by this f and x. And then we say that phi minus is a strong global subsolution if we can find a certain radii to construct balls in our functional spaces, so that phi minus is a subsolution that works for any y in these balls. Okay, so this subsolution is uniform within certain balls in our functional spaces. So that is our idea of a strong global subsolution, and this is the idea is that this allows us to have this uniform control through the iteration scheme. And a global strong super solution is defined following the same lines, but with the opposite inequalities. As usual, we say that the barriers are compatible if they satisfy these conditions, so they have to be positive and the subsolution be not above the super solution. And now we have all the necessary tools to prove our main existence criteria. So assume that we have our asymptotic Euclidean manifold with our regularity hypothesis, recalling p greater than n, and delta in the right interval, so that we have isomorphisms properties for the linear parts of our system. And assume that the Lixovics equation admits a compatible pair of strong global sub and super solutions, phi minus and plus, which are respectively asymptotic to certain harmonic functions, here omega plus and minus, and this omega plus and minus tend to certain fixed constants at infinity on each end. And in this context, fix some harmonic function omega, which is asymptotic to constants which are in between the constants of the sub and super solution in each end. And further, suppose that the solution map associated with our shifted system, with the linear iteration scheme, is invariant on the balls where the sub and super solution work. These are the hypotheses. Then the system admits a solution and with the conformal factor being positive. And one thing that is important to highlight here is that this invariance property actually doesn't depend on the choice of our shifts. And this can be seen clearly because we have only introduced shifts in the Lixovics equation, and we are asking that the solution map is invariant on these balls here. And these balls are balls on the function spaces for the electric potential and the vector field X, where we don't have any shifts. So we will see when we produce barriers that this actually doesn't depend a choice of A and B. So the proof is quite long, but the main step are quite similar to things that we have been doing during our course. For the idea is first to introduce our shifts A and B in the Lechernowicz equation, so that the right-hand side defines a decreasing function on the conformal factor. We had some similar ideas when we were dealing with just the Lechernowicz equation. In this case, where the conformal, where the coefficients can depend on, can introduce coupling, the fact that we can choose these functions A and B is guaranteed due to the boundedness property. Then the idea is to start our iteration procedure. So we start, as always, with our subsolution. We fix some elements in our fixed balls for the electric potential and the vector field X. We use the linear properties associated with the operators P sub A, B in order to generate our sequence of solutions to linear problems, okay? And the next objective is to show that the sequence of conformal factors is actually trapped between our strong barriers. And the choice of our shift functions A and B, giving us these monotonicity properties, allow for an inductive proof which appeals to the maximum principles as usual in order to prove that this is true. This is all explained in detail in the lectures and follows along the lines of things that we have explained in detail for the Lechernowicz equation alone. And then the final objective is to show that our sequence admits a conversion subsequence to some element here in this space. In order to do this, first we apply, as usual, elliptic estimates to our sequence of solutions, and we want to know that they are uniformly bounded to use some compactness argument. And in order to show that they are uniformly bounded, again, the boundedness property becomes essential. And this shows this boundedness, that this sequence is uniformly bounded. Then one appeals to this compact embedding for this choice. And this is put together for with our compactness property on the coefficients in order to extract a conversion subsequence in the right space. And once we have this, then we appeal to the continuity of the operators involved in our system in order to show that the limits of this conversion subsequence actually solves our problem. And since our conformal factor is bounded by our strong global subsolution, it is positive and we have a solution to the conformal problem. Again, the details can be consulted in the lecture notes. And we have once more reduced our task to that of finding appropriate barriers for our system. So we will sketch how to do this in order to produce far from CMC solutions in the case of Yamabe positivity. We again have to highlight that the Yamabe class of our metric is going to be very important in order to get these constructions. And the Yamabe positivity, let us recall that guaranteed this property here. Basically that this operator is an isomorphism for these choices of parameters. And this is what allows for the far from CMC construction. Also, let us recall that our data theta minus and tau are actually linked if we want the solution to satisfy marginally trapped conditions. And the construction of far from CMC barriers is given in this lemma. So we have a Yamabe positive asymptotic Euclidean manifold with our regularity assumptions. We consider our system. We impose this condition on the data in order to satisfy the marginally trapped condition. We have to prescribe our function V. And then under a smallness assumption on the remaining coefficients of the system, not the mean curvature, on the smallness coefficient on the system, then the Lechernowicz equation associated with the coupled Einstein-Maxwell system for a charged perfect fluid admits a compatible strong global sub and super solutions. And furthermore, the solution map is going to be invariant on the balls where these barriers work. And the construction of these barriers is quite long and delicate. It can be consulted in the lecture notes in detail. We're just going to outline the main ideas here due to time constraints. And the idea is that appealing to Yamabe positivity, one can present a one-parameter family of strong global subsolutions that have this form, where alpha here is a constant. And omega is always a harmonic function with certain prescribed asymptotic behavior and with Neumann boundary conditions. And this is going to be a subsolution as long as alpha is below certain threshold. And what is important here is that these subsolutions actually work for any f and any x. So they don't impose any kind of restriction on the radii of our balls in our functional spaces. Good. And the Yamabe condition is needed because the subsolution is constructed as a solution of a certain PDE problem, which is guaranteed to have solutions due to our condition here that is given by the Yamabe positivity. And after that, the idea is to introduce a one-parameter family of candidates, strong super solutions that have this form. They are also constructed as solutions of an associated PDE, where we can prove some positivity due to the application of maximum principles. And this beta is also a constant. And we have to make these two barriers compatible. So one can do that by choosing alpha, that alpha could be as small as we wanted, to be below this quantity here. And this is positive since we know that both the numerator and denominator are positive functions. We tend to positive constants at infinity, so they attain, they are continuous, and they attain their minimum values, which are positive in the interior of the manifold. And therefore, we can choose alpha small enough so as to make both barriers compatible. Alpha is going to only be fixed after choosing beta. We still have to choose beta so as to make our candidate super solution an actual super solution. And also we have to fix the radii where these super solutions are going to work. And this is our choice of radii, which are going to be beta dependent because they involve the super solution, which involves beta. And they are clearly arising through elliptic estimates. In particular, these constants C and kappa are constants that arise through a priori elliptic estimates associated with the electric and momentum constraints. And so since we are using the super solution in this construction, this is going to be key in order to guarantee the invariance property. Because due to the elliptic estimates, any solution to the linear problems that is constructed from some phi that is below phi plus is going to be below this bound that you attain via the elliptic estimates. But again, these radii are all only fixed after fixing beta. And then once we have that, we choose our balls in our functional spaces with this radii, and we need to fix beta. Okay, so this is what we were saying, that with this choice for these balls, given any elements in these balls, f bar and x bar, if we consider some phi bar that is below our super solution, it follows from the elliptic estimates associated with the electric and momentum constraints that the solution map of our shifted system that takes this phi bar, f bar, and x bar to the corresponding solution of the associated linear problem stays inside these balls. Okay, and here again, this is the remark that we were making. This doesn't depend on A and B. So this implies the desired invariance property. And what we need to show now is that we can choose beta so that our phi plus is actually a strong global super solution for these choices of radius. Good. This last step is achieved appealing to elliptic estimates, embedding properties of our functional spaces. and by imposing smallest conditions on the rest of the coefficients of the system, that means not for the mean curvature and the derivative of mean curvature, but for the rest of the coefficients of our system. So with that, this last step is the one that takes more work, and it can be consulted in the lecture notes and in our paper. But with that, we can provide, after imposing the smallest conditions, beta sufficiently small so that the construction works. And then we have a fixed beta, we have fixed alpha, we have fixed our radii, and we have our barriers. And using these barriers, we can apply the main existence theorem. And one thing that we have still to guarantee is that this a priori bound is satisfied. And basically, the idea is that under close inspection, one can see that the above construction works if one fixes a priori V equal to the super solution. But this is at the expense of demanding that this difference has to be small enough. But therefore, is imposing a smallest condition on this quantity and taking V as the super solution, the construction of the barrier works. And clearly, if B is the super solution, then we know from our main existence result that the associated solution is going to be below phi everywhere, in particular along the boundary, and so this condition is going to be satisfied. And therefore, we can establish the following theorem. We have a Yamabe positive asymptotic Euclidean manifold with compact boundary with our regularity conditions. We consider our constraint system. We set everything in the right functional spaces, and we have to demand that certain coefficients here satisfy this relation. This has to be non-negative associated to the marginally trapped boundary condition. We fix our theta minus to be negative. And then we have to impose smallest conditions on all these parameters. So in part of the fluid parameters, in part of the boundary conditions, on the magnetic parts, on our TT tensor, and on this difference between the theta minus and tau along the boundary. If they are sufficiently small, then we have a solution to the conformal problem that is obtained using these barriers and then applying the main existence theorem. So we can construct far from CMC solutions for a charged fluid on asymptotic Euclidean manifolds with marginally trapped boundary conditions. And this is basically going to be the last result that we're going to present in this course, where we have been able to start with some simple constructions associated with just the Lichtenberg's equation, completely coupled and closed manifolds, and grew from there to analysis on asymptotic Euclidean manifolds, and then the coupled system on closed manifolds, and then these fully coupled systems that add constraints on asymptotic Euclidean manifolds with boundary conditions representing black hole initial data. And in this context, let us highlight that in the case of other Yamabe classes, there are corresponding results, but they also demand a near CMC condition. But in this case, we also would like to point out that even this CMC and near CMC case should be understood in light of the comments that we made at the beginning of this lecture, the fact that our system is completely coupled even under CMC conditions. So it's not like the near CMC condition is as strong as in the case where it allows us to completely couple the system. Okay. And again, as is typical for non-CMC constructions associated to the constraint equations, we don't have any kind of claims about uniqueness. It is an important open problem, and also an important open problem is related to results for general data without smallest conditions. And these kind of results don't seem to be attainable within using current techniques, and this is part of an ongoing research program. And both these problems are related with the objective of using the conformal method as a way of parametrizing the space of solutions of the constraint equations. So they relate to ongoing research. And I hope you have enjoyed the course. We're going to stop here. I thank you very much for your attention. And any questions and comments will be most welcome.